Welcome to another unit in this methodology toolbox. This time I want to talk about quality measures which are important when you perform a regression analysis. Here we can differentiate between three groups of quality measures. The first one applies to coefficients. So if I want to check whether particular variables are of relevance. Here I can start with the standardized coefficients, which simply tell me which of the variables has the strongest, the weakest impact of all of them. So this helps me compare variables against each other regarding their importance. If I want to know whether they are important enough, relevant enough to be kept in the data set, I can refer to the t-test, which tells me whether the coefficients are significant, meaning whether they are different from zero, meaning that the underlying variable actually plays an important role in explaining the dependent variable. And finally, I could consider the variance inflation factors, testing whether I have a certain problem with multicollinearity. If this is the case, I can try different contexts like testing for moderating, mediating effects, or I can simply exclude them from my model. Well, those are three aspects regarding the coefficients, single variables. I can, however, also discuss measures considering the overall model quality. Here I first start with the coefficient of determination, the R-squared. And well, I have two additional comments here. I talked about the coefficient of determination, which tells me the share of dispersion of the variance of the dependent variable which my model explains. But I could also use the corrected version. The corrected version corrects for how many variables do I have. If I include additional variables, R-squared will always increase or stay the same. It will never decrease. However, it could be that I add a lot of irrelevant variables to my model, which do not add anything to it, make it only more complex. In this case, R-squared might be the same, but if I use the corrected R-squared, this will decrease. So I should only include those variables which also increase the corrected R-squared. I also have here the so-called pseudo R-squared. That's the case if I work with a nonlinear regression analysis. In those cases, usually no R-square is available, but there are some approaches, as with logit probit or ordered logit probit, where you get an alternative R-squared. It's calculated similarly to the R-squared, but it's slightly different. Those ones are called pseudo R-squared. For example, the one by Nagelkirchen. Okay, in accordance to this just tells you how much of the variance can be explained. If you want to know whether this is a significant amount, you can run an F-test, or again, if we do not have a linear model, this might be replaced in some cases by a Waltz chi-square test. This just tests whether your model has enough explanatory power. And then we have standard problems, which we should test for. I already mentioned for the coefficients, the multicollinearity problematic. Regarding the full model, I could test for heteroscedasticity. Or is the dispersion equally distributed across the whole data space? This I can test with the Breusch-Pagan test. If this is a problem, I could simply use Robert's standard errors. In addition to heteroscedasticity, I can also correct or test for autocorrelation. Are the residuals dependent on each other? So can I assume that there is an additional link between my dependent variables? It could be tested, for example, with a Durban-Watson test. Or if I'm focusing more on spatial autocorrelation, so for example, there's a spatial geographical, whatever background, linking the different variables, especially the values for the dependent ones. That's what, as one test, the Morans I test tells me. Do I have a problem with this? Should I include spatial effects in my model? Then finally, a lot of approaches require normality, normally distributed, that's the important thing, residuals, not necessarily variables. If I want to test for the normal distribution of my residuals, I can use the Jark-Barra test. This tells me whether the regression I perform is actually usable. So that's 6 measures working on the whole model, on the quality of the overall model. However, I might also be interested in comparing different models, the quality of different models to each other. Of course, I can use aspects like the R-squared, I could use the F-test value, something like this. Or I could run specific tests, use specific statistics aimed at comparing different models. The first 2 ones are the Schwartz, the Akaike information criterion, similar to the Bayes information criterion. They are just values, statistics, which you can use to compare which of 2 models, which of a number of models is superior to the other ones, has a better overall quality, fit, whatsoever. In addition to this, you could also run a Hausmann test, comparing the models, actually having a test which of the models is better suited than another one. For example, this could also be used if you want to know, when you work with panel data, can I use a fixed effects model or a random effects model? So that's the final 4 comments if I want to compare models. Of course, I can calculate all the information criteria also for the models in general, but it mostly makes sense to use them in comparison because they cannot really be interpreted as understandably as, for example, the R-squared. Well, this already brings us then to the end of this session. So I hope you enjoyed it. I'll say goodbye and see you next time.